and sediment water, that's also 2. So, roughly 2 hours in this lecture. And let's start with air-water exchange. Is there a clock here? Oh, there, yeah, I cannot see it. So, when it's time, you just raise your hand, right? So that I don't have to pay attention to it. So if you see that it's 4:30, then you just raise your hand. I know because it's so many hands that it's not a question, but it's just time for a break, right? So that's a good deal, I hope. So one of you will raise his hand and then the rest just will follow. Let's see if this works. No, that doesn't work. So I will do it the old-fashioned way. Yes, that works. So air-water exchange of what? Well, of chemicals. Now you know ions that are in the water, they will not just go into the air. They are dissolved in water, so they will not go out. However, gases like CO2 and volatile substances that are in the water, they will evaporate and go into the air until there is some equilibrium attained. And vice versa. If you have a chemical in the atmosphere, it will just go into the water until an equilibrium is achieved. Now these graphs over here, let me see if this works. No, it doesn't work. So, maybe there's one on off switch. No, that's not. So, but you see a straight line, right? In this blue upper graph, on the axis, it is horizontally the pressure in the atmosphere, and vertically concentration in the water. Now, if you have these chemicals at start, you will not have this. But after some time, in an experimental setup, or just in the environment, you will have equilibrium. And then there is a straight line. There is a linear relationship between concentration in the water and concentration in the atmosphere. And the second graph illustrates the same thing. Just a linear relationship goes through the origin, so it must be a constant ratio. And that's also the slope of this line. And then the equation for this is P equates to H times CW. And that is referred to as Henry's law. P for partial pressure, CW for concentration in the water, and H, the first letter of the guy who came up with this, Mr. Henry. So, Henry's law constant. Now the units, pressure in atmosphere, concentration in the water, in mole per cubic meter. And then this gives, logically, the units of the constant. And you can just calculate that or show it on a piece of paper, but it's written here already. Then the unit must be atmosphere times cubic meter per mole. Now, you can use other units for CW or pressure, then the units will change. As long as you are consistent, you can also use other units. But this is what you see most often. In the literature, you also sometimes find the so-called dimensionless Henry's law constant, without dimension. And this can be derived as follows. Maybe you remember this law, left-hand side upper corner of the sheet, the slide, P times V equates to nRT. Does anyone know the name of this law? Sorry?
Ideal gas.
Ideal gas law? Yes, it is the ideal gas law. Boyle's law? Okay, you stuck? Ring a bell? No, it doesn't ring a bell. So let's leave it at the ideal gas law. So this is the ideal gas law. So P for pressure, V for volume. And so this classroom, huge classroom, there is some pressure, it has a volume. And there is a number of moles gases in this classroom, which is N, and then it has a temperature in Kelvin, that's T, and N is just the number of moles of the gas in this classroom. Now you can do that for any volume, of course, or any number of moles. And this is the law. Okay. Now we use it to convert Henry's law with dimensions into a version of Henry's law constant without a dimension. And how is this done? If you take n over v in that equation, n over v, then you get p over RT. I don't have a pointer, well I can show it here. So n over v equates to p over RT. That's the same as this law. And so you divide. Did I do that? It's magic. Wow. Okay, it's my first time in this class. So, a rearrangement of this equation is here. Now, n over v is number of moles in a volume, and number of moles divided by a volume, by definition, that's concentration, right? Concentration is just chemically the number of moles of something divided by the volume. So n over v is concentration, and here we have p over RT, that follows from this law. And then for this p now, we can substitute Henry's law that we had from the previous slide, because we want to get rid of the p. And then we get this equation, Ca in yellow, equates to h over RT times Cw. So this is still the same Henry's law, but we got rid of the pressure. And this is done using the ideal gas law. If you roughly understand it, that's fine. If you understand it completely, it's fine. If not, no worries. Forget about it. Just read it at home. But believe me, by combining this simple equation with the previous one, Henry's law, you get this one. And that is that's a concentration in the air, moles per unit of volume, concentration in the water, same unit, mole per unit of volume. And then, therefore, this is dimensionless. So h over RT is dimensionless. And that is referred to as the gas-water partition coefficient, KAW. So KAW is a dimensionless Henry's law constant. So this is all a matter of definitions and introduction to air-water partitioning. So all gases strive at such an equilibrium. Now, is there equilibrium? Not very often. Most of the times there's transport going on. So the environment is rarely at equilibrium or steady state. And then this is a model by Mr. Whitman, the Whitman model. And it's quite helpful to understand the kinetics of air-water transport. In this graph, the upper graph, you see in the middle of the graph a vertical line. That's the air-water interface. So normally it's horizontal, right? But it's tilted here. So for convenience, the water is at the left-hand side, as you can see, water. And the air is at the right-hand side. So here it's water, here air. And in the middle is the actual interface. Now, this water has a certain level of turbulence, but close to the real interface, the water is more stagnant. And that's this layer. It's a relatively stagnant water layer. It's to do with the forces of the water molecules close to this actual interface. So, a stagnant water layer. Similarly, at the air side, there also is a semi or more stagnant gas phase. If a gas wants to penetrate this layer, actually it has to pass this stagnant air layer and then this relatively stagnant water layer. And you can imagine maybe that if the turbulence in the air is higher than in the air stagnant layer, and the turbulence in the water also is higher than in this water film, stagnant water layer, that therefore the resistance to transport is not in here and not in there, it's here, because these layers are relatively stagnant, so it takes more effort for molecules to pass these layers. You may even already, probably intuitively understand that it's not very likely that for a given gas molecule, this layer is of equal resistance for that molecule than the other layer. Probably one of them plays a bigger role than the other. So that is the use and the benefit of this model, and it makes visual how this transport works, and if we are to understand the kinetics of air-water exchange, we have to think about those two stagnant layers. Still, it's a model. Now, of course, this was a course about quantification, so we want to be able to calculate the rate of transport. Therefore, you see in the white block below the graph some equations over here, and these are so-called flux equations. The flux is just the mass of a chemical passing the surface area per unit of time. So in a minute, in this surface area, if this were our interface, you could think of chemicals going through this area per minute. Now let me explain here. You see three different parts in this equation for the flux. Now the flux here is mole per square meter per day. But same story, you can also do it per hour or gram or whatever. Here it's mole per square meter per day. The whole idea of the flux is that you need a concentration gradient, otherwise there is no flux. If the concentration here is the same as here, or is at equilibrium, then there will be no transport because there's equilibrium. So you need a gradient. You need over equilibrium or under equilibrium. So here at the left-hand side, you see a partial pressure here at the true interface and a partial pressure here. And if that's different, there's a difference, then actually you have this gradient. And then you have to multiply it with some constant, K, capital K, and it carries the subscript G, that is the mass transfer coefficient for penetration of the gas film. And it has unit meter per day. So it actually is a speed, meter per day. All right, now there's RT here. RT is always just to get the units right, because we equate it here later to concentration, and this is in the gas phase, so we again need this RT. It's the same story as with the ideal gas law. Now, if a molecule passes this series of films, then you can safely assume that whatever goes in here comes out here at the middle, goes in here again, and comes out there again. So the flux through this first film must be equal to the flux in the second film. And what goes in goes out, goes in again, and goes out. The assumption that we make here, that there is no source process in between, or there is no loss process. So there is no loss of the chemical here. And so we assume it's conservative mass transfer, what goes in comes out, or from the other way around, also possible. Therefore, these two fluxes, the flux gas film, flux water film, must be equal. So we put an equal sign. Now you can probably also intuitively understand that if we can express the flux equation in terms of difference in pressures here, and for the water film, a difference in concentrations there, somehow it must be possible to also express the flux in terms of a concentration here and a pressure there. And then of course you need to make some corrections. So actually it's a combination of these two. And that's done here. Concentration in the water minus the partial pressure divided by H. Because if you divide by H, Henry's law constant, you convert the partial pressure to the equivalent value in the water phase that you would have if there were equilibrium. So P over H is the value that you would have if you would have equilibrium. So if P is not at equilibrium, then there will be a negative or a positive number here, and you will have a flux. And then I forgot to tell this, for the liquid film, K carries the subscript L for liquid, and this K does not carry anything, it's the overall mass transfer coefficient. What determines the mass, the magnitude of the mass transfer coefficient? Well, you can imagine that you have small molecules and you have huge molecules, so there is some diffusion underlying this K. And so there are equations that say K equates 2, and then there is a diffusion coefficient in water. You can also imagine that if the liquid film is like this, or like this, that it can make a difference, or the viscosity of the fluid. So for some reasons, water, if there are other things dissolved in it, could be more viscous than in other situations. All right, so far so good. This capital K can be related to this KL and this KG according to this equation over there via this equation. So the reciprocal of capital K is related to the reciprocals of the mass transfer coefficients for the liquid film and for the water film. What could you imagine is the reciprocal of a mass transfer coefficient? Well, please remember a mass transfer coefficient actually is a speed. The unit is meter per day. So the reciprocal of that is day per meter. How many days does it take to travel a meter? And if that number is high, many, many days to travel a meter, then apparently the resistance is high. So this reciprocal of K, you can think of as a resistance, the difficulty to pass this barrier. So people talk about the overall resistance, 1 over K, or the separate resistances. And here you can see from the equation that in a way this overall resistance is just the sum of two underlying resistances, the resistance in the liquid film, resistance in the gas film. And obviously, dependent on the numbers, one of the two could dominate. And that is actually quite often the case, which makes life easier. Okay, so now some slides about this overall resistance. So it's resistances in series, and in this table you see a couple of substances that can pass these layers, and you see that the Henry coefficients differ enormously, orders of magnitude. For nitrogen, the first one, it's 1.6 atmosphere cubic meter per mole. However, for phenol, the lowest one, 1.8 times 10 to the power of minus 7. So that spans 7 orders of magnitude. And the others are in between. Now, and you see at the left-hand side in the equation that the Henry's law constant is in there. So if, for instance, Henry's law constant is very, very, very small, like for phenol, it's divided by H. So for phenol, that term for the resistance in the gas film becomes much higher relative to, for instance, nitrogen. So these Henry's law constants are in a way weighting factors in this summation for the importance, weighting factor, of the gas film resistance. Now, some numbers. So roughly, for many gases, KL often is around 0.1 meter per hour, Kg 20 to 60 meter per hour. The value of RT is known. We take room temperature in Kelvin. R is the gas constant. I think it's like 8.314 something. You probably remember this value. And then dependent on H, you can just calculate that when H is higher than 10 to the power of minus 3, then the overall resistance is in the water film. And if it's smaller than 10 to the power of minus 3, the overall resistance is in the air. So if it's very small, if H is very small, the resistance, then this gas film resistance becomes important. That's what I already explained, because you divide by H. So this is a handy rule of thumb. If you think of a gas and you know the H value, Henry's law constant, then you can know where the resistance is. So, coming back to this table, so for nitrogen, oxygen, and carbon dioxide, the resistance in the water is dominating the transport, and for the other, it's the resistance in air. Okay, you might think, so what? Well, of course, if you're a scientist, all these mechanistic things are interesting, but if you take it from an application point of view, think of a liquid film, then it's properties of the water. So maybe the flow or the roughness of the water surface could affect the thickness of the film. If it's in the air, so the air side stagnant film, then maybe other conditions, weather conditions might be important. Alright, so that was the first part of this lecture. And now we go to the second part, which is about reaeration. Reaeration is just also air-water exchange, but it's specifically for oxygen. And for water quality managers, oxygen, of course, is very important because we want to have our surface waters with sufficient oxygen because it's needed for all kinds of ecological processes. So you see an ecosystem and a surface area, and if there is a shortage, if there is a deficiency of oxygen in the water, and we know that in the air there is plenty of oxygen, then there will be transport from the air, from the atmosphere, to the water. And this is referred to as reaeration. So there was air in the water, for some reason it reacted away, it's gone, and then we have reaeration. So then we define something which is referred to as the oxygen deficit. Well, what's that? There is a maximum concentration of oxygen for water. It cannot hold endless concentrations of oxygen. There is a saturation value. So we say that if actually the concentration in water has that saturation value, then the deficit is the zero because it's saturated. And if there's less oxygen, we have a deficit, right? So if the saturation value is 8 and you measure 7, the deficit is 1. And then you will have transport. So the saturation value is denoted CS, S for saturation, and CW, the actual concentration. So it's written here on the slide, right-hand side, lower corner, CS minus CW. Then we use a flux equation like we have seen before. So the flux of O2, again, is just a mass transfer coefficient, KL. Why KL? Well, we just saw 3 minutes ago that the resistance for the transport of oxygen was in the liquid film. So for oxygen, we simply forget about the Kg. KL is important. And then instead of the concentration difference that we had in the previous equations, we now use the saturation value minus CW. That is what we use as an expression of this gradient that we always need for transport. Now, for many purposes this is enough. However, for applications or other purposes, we prefer concentrations, and a flux is not a concentration. A flux is mass flowing through a surface, horizontal surface in this case, per unit of time. So if we just divide the flux by depth of the water body, we have concentration. And because flux is per surface area, so that's square meter, a certain surface. If the lake below that surface is 2 meters, right, we just divide by 2, and then we have a concentration in terms of flux rewritten in terms of concentration. So by dividing by h, flux changes into the differential equation dc dt. So please note that h here is depth. It stands for height, not for Henry's law constant. We cannot change this. Sometimes letters are used for different things. So from the context you have to understand what it is. Now I think this speaks for itself, differential equation. I just explained that Cs minus Cw, that's the saturation value minus the actual value, is referred to as the oxygen deficit. Now we can abbreviate that by the letter D of deficit. So nothing is happening here mathematically. It's just renaming. So we can replace Cs minus Cw by D, and then you get the equation here where it's expressed as D. You can solve it analytically, and then you get this simple equation. D equates to d0 times e to the minus kat. First order kinetics. Now, I uploaded this file on the Blackboard. I hope you by now all have access to Blackboard. I checked a couple of things yesterday and this morning, and somebody that I registered still. So you can take a look, but it's also in the reader. And then the oxygen concentration over time. If you would have a water without any oxygen, then this differential equation and the analytical solution just predict a curve like this, first order kinetics, and the steepness of the slope, so how long it takes before you reach saturation, is determined then by this Ka, the reiteration constant. Is there any question about this?
Yeah.
Yes?
I have a question. Why the layers in between two films are stagnant?
Yes? Why are they stagnant?
Yeah.
Okay, that's a good question. So maybe I was not completely clear, but I hope I said a couple of times like relatively stagnant. These molecules in the film, they are not fixed. They will always move due to the Brownian motion, and there's always some turbulence, but it's a very thin layer, like maybe 20 micrometers. So there is not much room for the larger flow patterns. It's all very small and on a molecular level. So it is not fully stagnant, but it's relatively stagnant. And relative to what? To the bulk water. The bulk water is just a river flowing, for instance, or with all kinds of eddies and turbulent flow patterns. So that's hydrodynamics, it's another course. But so not fully stagnant, but relatively stagnant, because in the bulk water, the molecules, the water molecules are just seeing each other. But at this interface, the motion is restricted. And there is some sort of a friction of the water molecules at the actual interface with air. Because water molecules, they like each other. They can form hydrogen bridges, all kinds of interactions. But at the surface with air, there's neutral gas molecules, like nitrogen and oxygen, and they cannot move as freely as they can in the bulk water. So that's why this relatively stagnant layer is formed.
Then it means no transfer, no mass is transferred in between the liquid film and the gas film.
There is mass transfer in the liquid film and in the gas film. However, the molecules of those media themselves, so the gas and the water, are moving at a slower rate. And so you can imagine that if water molecules are moving at a high rate and there is a chemical in there, it also is transported at a high rate. The mixing is higher. But if the water itself is more stagnant, then the chemicals inside that water are moving slower. Imagine a block of ice and you put a chemical on top. It takes a long time before you see that chemical at the bottom of that block of ice. If you take a bucket of water and you put the same chemical on top of a bucket of water, after some minutes you already see it diffusing and dispersed, due to dispersion, and maybe after an hour you see the color of the chemical maybe at the bottom of the bucket. Because ice is restricted water, cannot move freely, whereas liquid water can flow freely. And it's a similar situation here, although of course the liquid film is not as rigid as a block of ice. Is that a good explanation?
You mean that the mass is transferred to the fusion?
Yes. Yeah. Mass transfer due to diffusion. Maybe I didn't say that, but I think I used the word diffusion as something underlying the K value, but the transport inside these layers is by molecular diffusion, actually. Yes. And so it's like concentration here and there. If it's higher here, then we will, due to the diffusion, Fick's law, the chemicals will go to the concentration, to the place where the concentration is lower until there is a steady state. Yeah? All right. I see no fingers yet, so apparently there's still time, a couple of minutes. So reaeration, and then yeah, this is my final slide, so good planning. But it's a complex one. So, but let's give it a try. So how can we measure reaeration in a water body? In a lab it's easy, you just have a bottle of water and you take an electrode and measure the oxygen. But in a natural water body there are other processes going on than reaeration that also affect the concentration of oxygen in the water. So we have to correct for that. So imagine that we have a river stretch and that there is a point A in that river and a point B, and the water is flowing between A and B from A to B. And the flow is a bit patchy, you can see that. And you want to know how much reaeration takes place, or what is the reaeration coefficient for the river stretch between A and B. How would we do that? Well, you could say, well, we measure oxygen in A and in B, and we know the time the water takes from A to B. So if the oxygen is more or less, and we have the time, we can use that same model, the first order kinetic model, and then we can fit Ka. Now that doesn't work because there are other processes, as I said, that affect the oxygen concentration. Namely, mixing, dispersion, air-water exchange, respiration, that's a biological process, primary production, the sediment oxygen demand. So there's more. So what do? Then we inject in point A a chemical like, for instance, ethylene. And ethylene is then also measured at point B. And ethylene does change its concentration due to, it's listed there, mixing, dispersion, and volatilization. So the component of the oxygen change, the oxygen concentration change, due to dispersion and mixing, then also is captured by ethylene, assuming that oxygen and ethylene have the same extent of mixing and dispersion and volatilization. So actually the trick is, instead of oxygen, let's calculate the reaction constant for ethylene. Because ethylene is not affected by biological processes. There is no primary production of ethylene. There is no sediment oxygen demand for oxygen or ethylene. The only problem remaining for ethylene is that it can change its concentration due to mixing.